Okay, so the previous video seems to have cut out at 53 seconds, so I'm going to try and just do a quick recap of what I tried to do in that last video, which was to really just visualize what we've done here. So first thing I just want to maybe just highlight here in this solution that we went through. So make sure where I can find this now. Yeah, here it is what I want to be able to talk about. Okay. Force. Okay, so this is all right. So we spoke about the displacement field being quadratic. We spoke about strains then being linear. We spoke about the stress expectation being linear as well. Then, because of the fact that the Young's modulus is just a constant in this case, it's not something that is also varying spatially. The one point I rushed a little bit last time, and I think that was still within the 53 seconds, but I'm just going to mention it again, was just this discussion about what our expectation would be if we were to compute sort of the internal force of the structures. If I were to make a cut anywhere, and I ask you, but what would that force be that acts on there? Or if I can make a cut here, what would that force be from a finite element point of view? Okay, so what would my expectation be from the finite element point of view? Well, the fact of the matter is we know that we can compute that internal force as sort of the integral of the stress over an area, and if in this 1D case we can make the assumption about this uniform kind of distribution. But essentially, it would just be the stress multiplied by the area in this uniaxial kind of case. And in that case, if you think about it, and I tell you, well, my expectation would then be that my force should be something that varies quadratically. And the reason for that is that I know that the stress is a linear variation, and I know that the actual force, the area has also linear variation. So it's a linear term times a linear term. I expect maybe to see something quadratic. The only way I would not see a quadratic is if for some reason this quadratic term would have a zero coefficient. Then I could maybe just see only linear variation. But in general, if I have two linear terms and I multiply them out, the resulting response would be something that looks kind of quadratic. So that would be my expectation of the internal force from a finite element point of view, is that I would like to see something with a quadratic variation. But if I were to ask you from a structural mechanics point of view, if I were to make a cut anywhere, what do you expect the force to be? So if I do a free body diagram, cut it here and say this side we have F 1,000 newtons. What must the force be on the other side to keep it in equilibrium? Your expectation would be 1,000. It would be 1,000 right throughout. It doesn't matter which x you evaluated. You would expect to see a reaction force of 1,000 on the other side to keep it in equilibrium. This is again just demonstrating to you that we are not satisfying stuff exactly. We are satisfying things sort of in an approximate or an integral way. That is important to understand. And we can also see already from this, just by computing the internal force at various places, we can see already some variations. So if I compute the internal force at x equal to 0, 923 newtons. At x equals to 1, again 923. So I see sort of two equal values. Then at 0.5, I see a much higher value. And this immediately alludes to me or points to me to the fact that, oh, maybe what's going on here is the fact that that there's obviously not a constant. It's obviously not linear. It must be something else. And if you reason about it, you can reason out and say, I know for a fact that this is a quadratic relationship. Okay, so this is the kind of stuff that we need to be able to do in the finite element method, that we can reason about the fields that we are using to approximate certain quantities, and those approximations for the field have direct consequences on sort of the type of stuff we expect to see later on. So if I assume a quadratically varying displacement field, at best I can see a linear variation in strain. And if the Young's modulus is constant, at best I can see a linear variation in stress, for instance. So these are the things that I would like you to become comfortable with. So let's go and check out how this looks now in terms of when we visualize this now inside Python. So I want to go now to my Python notebook, and I just want to take you sort of through the expectations. So all I'm doing here is I'm coding in the Python explicitly. I'm not solving it now with SIMP or anything. We've solved it by hand, and I also want to encourage you, even if you solve things sometimes by hand, please go back to Python and visualize it. Spend as much time as you can to use Python as your calculator. The more you spend it in this course and in all your other courses, the more you'll get out of it for MRX 410, and the more you'll get out of it for MRN 412 and 422. The better research you can do, the better design you can do. So this is really, I just want to encourage you, this is your new calculator. It's not an HP anymore, it's now Python, and please make sure you use it, because this calculator will unlock doors for you when you leave university and walk into industry. Okay, so the bottom line is, there's my displacement field. I assumed a quadratic, so at best we can expect a quadratic variation, yeah, the most complex kind of shape we have. We could also maybe just see a linear variation had this been a zero coefficient in front of the quadratic, but it's not zero, it's some value in front of the quadratic, so that's why we see that kind of nice slight quadratic variation there. Strain, there it's coded, we can see explicitly it's linear. There's the stress, E times strain, and there I'm computing the internal force. And now I'm just visualizing each of these fields. So we can see the displacement field, we can now reason and say, does this make sense? Oops. Does this make sense? Yes, it's clamped here on the left-hand edge where it's supposed to be clamped. I can see sort of the right-hand tip displaces the most as expected because that's sort of the end on the other side. And so that all is as expected to see that this tip which displaces the most, it's displacing in the positive direction. We can then go and say, but can't we just sort of estimate? Is this even in the right ballpark, this tip displacement? So yeah, let's go do a hand calc. Let's do a sanity check, okay? So this sanity check kind of calculation, we could go and say, we could compute it from our relationship for a bar. And I'm just going to make an assumption now to say, to do an estimate, I don't want to now calculate exactly what the tip displacement, I'm just going to do a quick estimate by saying, let's assume the area is sort of a, we know it's a linearly varying area, but let's assume the area is sort of a constant and as the average between the large and the small side. So if I assume it's a 0.0015, that is sort of the average between the large and I can say, let's imagine the whole bar was just uniform, just to get a thumbsuck ballpark estimate out, okay? And if I do that, I can say, well, I can now use essentially this relationship to say the delta, the tip, so the displacement. Recall this from just the normal bar stuff you've done in MOW 227 and that we've did earlier in this year as well. Yeah, so you recall, so the force times the length of the bar divided by the area and the Young's modulus. That's a good indicator that we have for the tip displacement. Okay, so maybe you're used to it having this multiplied to that side to say P is a stiffness times a displacement, but this is essentially just rewriting it in this form, and I can then do this quick estimate and say, let's see if we trust the numbers. And if I do that, I see 1,000 times 1 divided by the area, which is now that average area for a constant assumption, and now 210 gigapascal, and I see by tip displacement, I expect to see about 31746. If I look at the tip displacement, if I now compute it, in this part, I'm just plotting now what I've evaluated here on a length space from 0 to 1, 11 increments. So the last value in this U that I would see now, but that I would compute would then be essentially this one here, and I can see that that ballpark is quite close. Okay, so that you see it's all in the same ballpark, so I trust the numbers. Yeah, so just from a quick stab estimate, I can say at least I know we're in the right ballpark. And this is the kind of stuff you need to be able to do. When I ask you in a semester test and exam, do you quantify for me, do you trust the numbers? You need to be able to do a quick stab verification estimate, a sanity check per se, just to make sure it works. Okay, so let's just look in more detail what I did here. I'm trying to post this video now before the half past, but I'm going to be slightly late for that. But all I want to do is let's quickly check here something. So let's quickly run through this, what is going on here. I'm using, did the hand calculation by hand, and now I just want to visualize what I did by hand. So I've got NumPy that I import matplotlib pyplot. So I'm just going to work numerically and not symbolically, just numerically. I say let's create a length space from 0 to 1, that's the length of the bar, 11 increments. It's a choice I make. I could make it 21, 31, 50, 101 if I want. That doesn't matter. Just where I want to evaluate, 11 should be sufficient just to get an idea of how the fields would vary spatially. Here's my Young's modulus. Here's my area now explicitly coded. So this is now a vector of areas for each of these x's. This is a vector of displacements for each of these x's. This is the strain, again, a vector of strains, a vector of stresses, a vector of internal forces. This is what I have. And now I'm just visualizing it, just saying plot x comma u, x comma strain, x comma stress, x comma internal force. So the strain as expected, I expect to see something linear. Yeah, that is fantastic. And let's reason about, do I trust, is this slope right? Should it maybe have been like this, or is this okay? Let's check. So at this place where this, on the left-hand edge, we know we have the most area. There I expect to see less strain. At the right edge where the area is the smallest, I expect to see the thing to strain, for it to have relative displacement with 2 points next to each other. It's going to be easier. So I expect to see larger strain there. So this is fantastic. So at the clamped end with a large area, I see smaller strain. At the small area, I see larger strain as expected. And that also translates then in terms of stress to say at the end where the area is larger, I see a lower stress. At the end where this area is smaller, I see a larger stress, as expected. Again, I can go and quantify, does these values make sense in terms of stress? What is the ratio of this to this side? Well, we can just do a quick sanity check to say the stress. If I look at the stress, essentially, oops, straight, I didn't run this notebook now. If I just compute the stress, for instance, here, where's my stress area? Which is the one? This is the one I'm trying to. So if I compute the stress, so that's not stress over an average area. So this is just to get a ballpark out. If I say, let's imagine somewhere in the middle, if I had sort of an area in the, halfway, like a average area, what is my ballpark stress I would expect to see on those plots? I can see it's about this value here, which is 6.7 MPa, let's say 7 MPa roundabout. So if I ask myself here, sort of in the middle around, what is that? Is that more or less 7 MPa? Boom, spot on, 7 MPa. That's fantastic. So I trust this kind of stuff that I see here. I can also just do another sanity check if I want to do it in different ways. To say, let's plot that stress vector. Where's my the stress vector? So I'm going to run this again. I'm a little bit sloppy here because I'm just overriding variables like stress here. I'm overriding. So if I plot this now, after I ran that first cell, I will see the stress vector now. And I can ask myself, what is this value equate to? If I take twice this value, do I get this value? And why would I like to see if this twice this value is more or less this value? Well, because the area on the left edge, the area here on the left edge is twice the area on the right edge. So if x is 0, then that's the area. If the x is 1, then it's exactly half of that. So I would expect to maybe see sort of a relationship of 2 between the two. And so that's in essence what I'm just demonstrate here is if f of a at x equals 0 I call small a, and at x1 I call it a over 2, I would expect to see a ratio of 2 between the two stresses. And I can indeed see that for myself. I'm getting that if I take this value here and I'm multiplying it by 2, I see that on the end where the stress should be larger, it's about twice that, the same as this value here. So all of these things check out. So these are just sanity checks, quick ballpark, thumbs up kind of estimates, just to make sure that we understand and trust what we see. So in the end, it's building trust, just to get an idea if we're in the right ballpark. If I look at the internal force, my expectation is not that I see a constant here. That's my expectation from structural mechanics and solid mechanics, but my expectation from finite element point of view is that I want to see something that varies quadratically because of the fact that I have a stress field that is linearly varying and an area that varies linearly. And essentially, that internal force is then the product of the two. That would be my expectation. Because of the assumption that I started off with by making that my displacement field is quadratic. That's where things start. That's where that drives sort of the type of solutions I'll get. But if I look at this and I say, look at that. So here on this side and here side, I underpredict. Here I overpredict. And only here at these two spots am I actually on what you would expect to see from a solid mechanics kind of solution. Only at 2 spots. But there's something beautiful I want to show you. If I were to do and say, let's integrate over this length of 1. Okay, and look at the average. Let's compute the average if I were to integrate this and see what is that sort of average force, internal force that we get. So some places I'm over predicting, some places I'm under predicting. But what would the average sort of look like? And I want to show that average is exactly 1,000 if I were to integrate this. So if I go and I say, let's do the integral. This is my area, displacement, and I compute the internal force. So here I'm just computing all of those values symbolically. So this is now sim pi again, not numerical, but sim pi. Here's my x symbol. X is not a vector anymore. Now it's a symbol. I run this and I say, that's fantastic. Let's integrate this internal force from 0 to 1. And luckily, because my integral is from 0 to 1, I don't have to rescale it. If it was from 0 to 2, I would have to scale because I integrated over a larger domain. So you can imagine if you want to visualize in your head, if I integrate the value 1, a constant value, and I integrate it from 0 to 1, versus 0 to 2. If I integrate from 0 to 2, that integral is 2. If I integrate from 0 to 3, that integral is 3. And if I wanted to get sort of an average out, I have to divide by that 3 to say what was the average value to get back to a 1. And so if I were to integrate that same constant value of 1, but let's say from 0 to 1, and I divide by the length of 1, I get back the average value. So the average and the integral is the same thing here, but what I want to show you is if I do this and I just integrate the internal force, which is this quadratic thing now, from 0 to 1, and calculate what is that average force that I get, I see it's exactly 1,000. Can you see that? So what I'm doing is I'm saying to you, I'm not satisfying equilibrium, because if I wanted to satisfy equilibrium exactly, the reality is this should have been 1,000 throughout, because any chop of that structure, and I create my small free body diagram, the two opposite forces must be equal to each other, so that it's exactly satisfied equilibrium. This shows you it's an approximation of equilibrium that's being satisfied, but it's such that if I were to look at the average force over this area, or that length of that bar, it indeed is 1,000 that I recover. So on average, it is actually in equilibrium. Okay, so this is just to conclude that. I'm going to post this video quickly so that you at least have this video to watch. I hope this audio is now working fine.